All right. Hey, moving on with our evolution unit, we're going to talk about some evidences for evolution. I don't know if that's the right right pronunciation of that, but we've made a lot of claims about how species change over time and how we know how old things are and um, origins of that kind of thing. And so it's time for us to make sure that we point out, exactly how do we know this? Because people weren't there. We can't. It's a slow process. It's hard. It's not impossible, but it's hard to see in real time or even within our lifetime. So we're going to go through a variety of pieces of evidence for evolution, starting with number one. That would be homologous structures. Remember that prefix homo means same or similar. And so these are similar structures anatomically, even though they have a very different functions. Okay, so I love this is my example here, and I love this one, is that every vertebrate on Earth, if they have arms, their arms follow the same pattern of one bone, the humerus, two bones, the radius and ulna, and then lots of little bones making up wrists and hands and fingers, etc. That's true if you're a human being. It's true if you're a cat, if you're a whale, if you're a bat, if you are a lizard, if you are a horse. Like I said, everything that has arms follows that pattern of one bone, two bone, lots of little bones. All right. Even though humans, cats, whales, and bats all use those arms for extremely different things, you wouldn't think if something was being designed, you wouldn't have the same bone structure for those four structures because there are very different functions you need to achieve for them. It's not how evolution works. Evolution has to build upon genetic material that's there in small mutations over time. And so, what's easier genetically to have happen? A misshaped humerus or a different size of humerus or a brand new bone altogether there. So, there's our example for homologous structures there. Number two are vestigial remains. All right, these are body parts that have little to no function in their current species. So it bears the question like, okay, like if that's just how that creature was, found on Earth, then why does it have these different things? But it's evidence that it might have been useful to an ancestor. So we see legs on a skink down here. Whales have this vestigial hip bone. There's no legs attached to whales anymore, but they used to live on land. Their ancestors did at least. So they have these. Humans, we have quite a few of these useless structures. Once again, begs the question of how did they get there? Okay, if you're being designed or if you're being, put on Earth as is, there's probably some purpose for these things. The purpose is it was useful to an ancestor of ours. A famous one is the appendix. Hangs down here off the large intestine. There's some evidence that the appendix still has some kind of function for us, but it's greatly reduced. If you're an herbivore, you have a very large appendix that's used to help break down grass. We don't do that anymore. So ours mainly hangs down there. It can kill you if it gets infected, but you can live just fine without one. Oops, where am I going there? Don't want to do that. Hate when I do that. Let me bring you guys back in here. Boy, really struggling. Okay, sorry about that. I am back here. All right, let's just go through all of them. Next one over here are the muscles around your ears. I don't know if you can wiggle your ears or not, but a lot of mammals can. Think about cats and deer and moose and whatnot. They can move their ears to help triangulate the where a sound is coming from. You have all the muscles to do that, and they still get signals to fire, but they're greatly reduced in size and diameter and strength, and so they're just kind of hanging out there. Wisdom teeth. If you're in high school, you're probably getting this age of if you're going to need to get your wisdom teeth taken out or not. As humans, cerebrums have grown, our jaws have shrunk, and so oftentimes there's not enough room in our mouths for all of our teeth, hence needing to get braces, needing to get teeth pulled, etc. If you look at your cat's mouth or your dog's mouth, they have plenty of room for their teeth. Why don't they have crooked teeth? They don't have the same issues that we do. We have vestigial remains of our tail down there. It's a fused tailbone. And then we have remains of an extra eyelid. Some animals have a third eyelid that rolls back over the eye, kind of giving it almost like a goggles appearance there. Good video in here if you want to check out some of those other vestigial remains that are interesting. Number 3 is embryology. All I have on this one is that roughly organisms start off their first several weeks looking exactly the same. So it's indication that the pattern to go from one cell to lots of cells is fairly universal across vertebrate life, at least. All right. That going from one cell to lots of cells, that first column, that first row up there, those are a variety of different organisms, but they all are going to start off developing very similarly. It's not until later on that they start to differentiate into their own beings, indicating that we're all connected in some way, shape, or form. You wouldn't think that development of a turtle, the first few weeks would be the equivalent of development of a human being. And then a big one, maybe the biggest one is fossil evidence. So I wasn't there, but on Earth, we have this large number of fossils that show animals that are extinct. They no longer exist. However, it shows similarities between extinct animals and animals that are alive today. We look at all those different fossils and then we put them on a time scale, aging the layers of the Earth, and it gives us this tree of life of how things have changed over time. Like I said, there are millions of extinct animals and fossils that we've found. The question is, if they're not, old ancient ancestors of ours, then what are they? They're just random fossils buried in the ground, etc. So it gives us an idea. How do we measure that? We measure that using radioactive decay. So I won't get into too much chemistry here, but different isotopes decay at different rates. We can measure this. We can use that to help age our surroundings, just like we saw with the aging of the Earth. And so we can give ages to rocks and then build a tree of life in that matter there. Like I said, radioactive isotopes decay at a constant rate and proportion to their concentration, giving us a half-life. And then lastly, I think we're 5 or 6 now. And this one is one that's still continuing to see new results, and that is DNA evidence. All right. As we dive more and more into DNA, we see more and more similarities genetically between species. We know that you and me and all humans share about 98% of the same DNA as a chimpanzee. We didn't come from chimpanzees. They're like distant cousins, but 98% of our genetics are exactly the same. But even all life, so you and a banana, 40% of your genes are roughly the same, because then a banana is made out of cells. It has cell parts that goes through the same enzymatic reactions that your cells do for the most part. So DNA is further linking the limbs on the tree of life as we continue to look at more genomes that are out there. So we are going to stop there for the day. That's a good place. And good luck on the follow-up questions.